All right, hello and thank you. Welcome to today's webinar hosted by EERI's Younger Members Committee. My name is Elizabeth Angel and I'm EERI's Communications and Program Manager. And before we get started, I just want to take a few minutes to talk about this organization if you're not familiar with us. EERI is the leading nonprofit membership organization working to help bring together professionals from a wide range of disciplines and fields, both in the US and around the world, who are all working to better understand earthquake risk and increase resilience. So if you're interested in joining us and finding out more about our activities, please check out the link to our website there. I will also share that in the chat. You can find out many ways to get involved and support our activities and participate. And one thing I particularly want to mention, for those of you who aren't aware of it yet, is that we are planning our 2024 annual meeting in Seattle for next spring in April. I'll share the link to the conference website in the chat later on, but we are planning both 2 great days of plenary sessions, special sessions. We'll be accepting proposals for those fairly soon, poster sessions. We're also going to have an earthquake reconnaissance workshop and a field training exercise, the seismic design competition for undergraduate students, and a lot more. So stay tuned for more news about that. So today I'm going to turn it over to Renmin Patel, who's an assistant professor at the University of Nevada in Reno and who is moderating this session for us today.
All right, thank you, Elizabeth. I'd like to once again welcome everyone on behalf of the EERI Younger Members Committee. It is a pleasure for us to see this great audience today for our 3rd YMC webinar. I will just say a few words about YMC. This webinar is an example of the several events that we conduct in our pursuit of fostering professional development. Other activities include professional workshops and also technical workshops and various annual meeting events. We have more workshops, social events, training, and so on. Some other of our YMC goals are to introduce younger members to leaders in earthquake engineering, and this is something that we are also doing today, to provide opportunities for younger members to serve on other EERI committees and initiatives. There are plenty, and to provide a platform for engagement of younger members so that the Institute EERI remains a vital organization. If you are interested in learning more about YMC, please get in contact with us using the email below or visit us at the website below. We will also share an interest form that you can sign up and join our YMC meetings that happen once the 3rd Friday of every month. All right, so without further ado, let's now introduce our first speaker for today. So our first speaker is Dr. Albert Kottke. He received his doctorate from the University of Texas in 2010, where he worked on random vibration theory site response. Dr. Kottke then worked as a postdoctoral scholar at Pierre on the NGA West 2 and NGA East projects. In 2012, he joined Bechtel to work on seismic design of nuclear and liquefied natural gas facilities. In 2010, he joined the Pacific Gas and Electric to work on seismic risk assessment and help manage the long-term seismic program. Albert, the floor is yours.
Thank you, Renmin. Hello, everyone. I guess I was going to say good morning, but it's not morning everywhere. So today we're going to talk about regional scale risk assessments, and this work was carried out by PG&E, but using consultants and researchers from a number of different groups. Those groups include Greenfield Geotechnical, Hashemi and El-Kharabi, Earthquake Engineering, Geoengineers, and the UCLA Garrick Institute for Risk Sciences. And I'll introduce the members of those efforts later on. Just before we jump in, I want to introduce PG&E for those of you who are not familiar with it. PG&E, or Pacific Gas and Electric Company, is focused on providing safe, reliable, clean, affordable electricity and gas to Northern California. We serve over 16 million customers over an area of 70,000 square miles. 16 million customers is about 1 in 20 Americans, which is a pretty big number. The service area that we have includes some of the areas with the highest seismic hazard in the United States. And so we have a lot of challenges of understanding seismic hazard, looking at seismic risk, and developing seismic mitigations. When we think about the scale of the assets that we have to manage, we have close to 20,000 miles of electric transmission lines, over 106,000 miles of electric distribution lines. We have 66 hydroelectric powerhouses that are fed from close to 170 dams. And we're generating something close to 4,000 megawatts of hydro capacity. So we've got a really diverse inventory spread over a really diverse area. And so we manage all of this using risk assessments. I work in a group called Geosciences within PG&E. Our group is about 20 or so staff, and our staff range from seismologists to geologists, geotechnical engineers, and structural engineers. We are basically internal consultants to the rest of PG&E to provide a constant cross-cutting geoservices group. So we support a wide range of projects from storm and incident response, where we may not know what's happening that day and what we'll be doing to support the company and our customers. And then we also look at long-term size research and implementation. And so projects might be years in the making or longer. Just a little note that we are currently looking for a staff level geotechnical engineer to join our group. Shown here is Diablo Canyon. The work that I do with the long-term seismic program supports Diablo Canyon through refinement of ground motions. And part of that funding was used for the project that we're talking about today, or projects. So why do we need regional scale risk assessments? For owners of lifelines, when we prepare for earthquakes, it really requires understanding of the entire system performance. And the system is complicated and is distributed over a wide region. When we think about regional risk assessments, they're different than, and risks from earthquakes, they're different than other risks. Another risk might be that we deal with at PG&E would be a dig into our either gas or electric lines, where we have really good historical information of how often people dig onto our lines. And that's why we have the Call Before You Dig program. For earthquakes, we haven't had an earthquake that really has impacted the East Bay for a very long time. And so we don't know how well our systems are going to perform without doing analytical risk assessments. When that earthquake happens, it's going to happen over a very wide region, and it's going to have multiple simultaneous failures. And again, we're not going to really know what that is unless we do these types of analytical studies. Regional models tend to be more approximate than a detailed engineering assessment at a specific facility, but they're still really useful to understand which risks are going to dominate, which assets are going to dominate that risk. But they tend to be much more simple, and their inputs are more uncertain. When we think about improving the regional response to earthquakes, we're going to rely on tools like these that we're going to talk about in the next by the next set of speakers. But they're going to involve a wide range of technical areas. You're going to see talks from people working in ground motion, folks working on geotechnical issues and building response. It requires coordination between a variety of asset owners. So at PG&E, I speak to folks that own electric assets, gas assets, corporate real estate, and they all have different priorities, and they all have different ways of looking at risk, and we have to provide a sort of a common language for that. But it extends beyond PG&E. When we think about regional risk, it's going to depend on other agencies and municipalities, and so the tools that I'm presenting today can help facilitate a common conversation on that. And these tools are the first step, and they're going to require continued maintenance and improvement, because we're going to only have one chance to really respond to the big design level event that's going to shake the San Francisco Bay. And we have to get it right the first time. And so we really have to be continually looking at this problem and improving the way that we do that. So for those of you that don't know, this is a shot of the San Francisco Bay Area, and what we've loosely defined the boundary. This boundary was somewhat defined on similar characteristics, population density, close enough in scale. that we can work in this space. It could be extended to include more communities, but this is our current definition. It's relatively small, but it has a high density of assets, both in terms of PG&E, but also in terms of customers. Additionally, there's a high seismic hazard. We have got the San Andreas and Hayward faults, as well as a host of other faults associated with those systems. And across the bay, we have a diversity of assets. We have flat areas that are dominated by soft soils, and we've got steep hills. In terms of PG&E assets, we have electric networks, and electric networks consist of transmission, substations, and distributions. And our transmission networks in the area consist of both overhead assets that are supported through towers, but also underground electric cables. We also have gas transmission and distribution, as well as facilities supporting those networks. And then we have buildings that sit over the areas. And just some numbers here, and we have close to 230 substations in the area, 830 miles of transmission line in the area, over 15,000 miles of gas distribution lines, and there's thousands of fault crossings in that gas distribution line. We have over 2,000 miles, or 2,300 miles of electric transmission, and close to 40,000 miles of electric distribution just in the San Francisco Bay Area. So we have a huge amount of assets that we need to think about. And we need to develop estimates of ground shaking and land failure to understand how these assets are going to respond to an earthquake event so that we can help mitigate and improve our system performance. To do that, we've been working on a number of tools to improve the way that we work in this space. And when Renmin asked me for this topic, I was like, this will be a great opportunity to sort of show this diverse pool of work. And these are sort of short glimpses into talks that really could be very much longer for each of them. So Mike Greenfield is going to be talking about an effort that was performed by him and a group from Infraterra on earthquake-triggered landslides and liquefaction. After that, Melanie Walling and Nico Kuhn are going to be talking about spatially correlated probabilistic ground motion scenarios. And then finally, Aladat Hashemi is going to be talking about building inventory risk assessment and looking at the relationship between these earthquake scenarios and how what would be done for a building-specific analysis. And with that, I'll turn it over to Mike Greenfield to talk about the earthquake-triggered landslides and liquefaction.
Give me a couple of minutes to just introduce you to the audience. I just want to remind everyone, if you have any questions, please feel free to send them using the Q&A button at the bottom of the Zoom windows. There will be time for answering these questions at the end of the presentation. Our next speaker is Dr. Mike Greenfield. He is a principal engineer of Greenfield Geotechnical in Portland, Oregon. Much of his research and consulting work focuses on regional scale liquefaction and landslide hazard analysis. Dr. Greenfield has recently completed several projects evaluating seismic hazards in the San Francisco Bay Area, as you will see in this presentation. Mike, take it away.
Thank you, Remnon. Thank you, everybody, for joining me today. I'm going to talk to you within the context of what Albert outlined about a tool to evaluate liquefaction and landslide deformation hazards within the San Francisco Bay Area. Albert defined the study domain that we're talking about, and it encompasses approximately 10,000 square kilometers throughout the San Francisco Bay Area, as I've shown here. So with respect to site-specific liquefaction and landslide hazard analyses, these are very well established and have been for several decades. At a specific site, a building, a single transmission tower, a specific element like that, to evaluate liquefaction, we would typically start with some subsurface investigation, including standard penetration test or cone penetration test. The image I have shown here on the left is a standard penetration test that's been instrumented to correct for energy. We also correct for other factors such as fine content. and overburden pressure. We make some assessment about the intensity of shaking that could potentially liquefy soils. This is typically done through code-based PSHA analyses or can encompass other types of analyses. And then we use simplified liquefaction triggering methodologies to evaluate the potential that the cyclic stresses in the earthquake could potentially exceed the cyclic resistance. Following the simplified procedure, we would then go and evaluate manifestation and deformation, the consequences of liquefaction. This is all very well established. Well, at a broad regional scale, like the scale of the domain that Albert's been talking about, we really can't rely on many of the assumptions that we utilize for site-specific analyses. It's absolutely infeasible to collect enough samples to evaluate subsurface conditions throughout that broad of a range. And in addition, different locations within the domain have spatial correlation of ground motion. So we can't rely directly on our PSHA types of analyses. With respect to landslides, we go through a similar process of evaluating site-specific hazards, where we would start with sampling and observation. I have an image shown of an inclinometer here on the left with a very discrete slide plane, so we would know kind of where the slide plane potential is or the deformation potential is going to be. We would do some sort of slope modeling, typically through limit equilibrium or finite element analyses, again, assess the intensity of shaking and use that information to evaluate deformation and runout. Again, at a regional scale, we can't really employ sufficiently dense samples. We can't study each slope in great enough detail to use our site-specific methods. So we have to make some approximations. Similarly, we can't rely on the same analytical methods that we use to evaluate slopes in 2D. So we have to do some simplification of the mechanics. We're also faced with the issue of spatial correlation at a regional scale. So how do we tackle this geohazard approach at a regional scale? So the key to doing this is start with our site-specific methods and then treat the inputs of those rather as deterministic values that you might identify from a subsurface investigation, treat those as random variables. So there's a great amount of uncertainty that comes with this, but it's quantifiable and we can step through the process of evaluating that. So the first step to do this is collect the available data, subsurface and geotechnical data within the domain. And this is typically the most time-intensive component of this type of analysis. We use that information to develop geology-based or spatially interpolated statistics with quantifiable uncertainty and variability. And that's the key. We want to measure how much we know and how certain we are of that. And once we do that, we can extend our site-specific methods with some probability theory to help us understand the potential for liquefaction, deformation, and landsliding. We also need to make some simplifications for the complex mechanics involved. So starting with evaluating liquefaction hazards, the first step in a liquefaction hazard analysis is to determine the depth of the groundwater. And over a regional scale, that comes with a very wide amount of uncertainty. So to address what the groundwater might be across this broad region, we take data from over 400,000 well observations and then develop a very simple finite difference model for the entire domain. So this is similar to what someone might do in a graduate school geotechnical class, albeit on a huge scale. That analysis, that 2D simple analysis, provides us with a mean function. And then we can interpolate the residuals of that mean function that's based on a physically reasonable groundwater surface with the observations from the wells in a process using Gaussian process regression to interpolate the residuals. We include both spatial and temporal dimensions in that analysis, such that we get a groundwater surface that includes both a wet season mean and a dry season mean, and some measure of the confidence of each of those. So we now have a probabilistic groundwater surface rather than the deterministic groundwater surface that you might enter in a simplified liquefaction hazard analysis. With respect to the cyclic resistance of soils for liquefaction, we correlate in this particular project, we correlate different geotechnical properties from SPT and CPT samples with the various geologic deposits. If you have very, very dense data, you could potentially interpolate these quantities within boreholes. But across such a broad region, we took the approach of developing geology-based statistics from a pretty wide set of SPT and CPT samples. You can see some of the quantities that we assess for various geologic deposits within the San Francisco Bay Area. So these are potentially for different types of fill within the area. And one thing to take away from this is that when we do this, we get probabilistic values associated with the soil behavior classification, whether it behaves as sand and is susceptible to liquefaction or clay-like behavior. And these differ somewhat significantly from what we might do during site-specific assumptions. So with respect to the figure on the left, for site-specific analyses, we typically assume that soils are either susceptible to liquefaction or they're not. It's a binary classification. Well, we have some uncertainty within a geologic deposit if we're going to encounter clay-like or sand-like soils. Also, with respect to penetration resistance, the uncertainty across a broad geologic deposit for penetration resistance is huge relative to what we assume for site-specific assumptions. And you can see the standard deviation of the data for the various geologic deposits on the right. So with those statistics, which we treat as random variables in a liquefaction hazard analysis, we can assess every location on a 10 by 10 meter cell for its unique geology, groundwater, and topographic conditions. When we do that, we can develop curves at each location for a range of peak ground acceleration and earthquake magnitude values. This is something that Melanie and team can use with their range of ground motion scenarios to predict the probability of liquefaction given a particular scenario. When we look at this result, the results of using expanded random variables and site-specific analysis, these actually compare very well with previous analyses looking at uniform geologic deposits under deterministic groundwater conditions. I want to add. So the dashed line in this figure on the left here is from the USGS, Tom Holzer and others. And in fill deposits around San Francisco and Oakland, it actually compares fairly well with previous analyses when we assume deterministic conditions for groundwater. As soon as we add the uncertainty in groundwater, this tends to change a little bit. I want to add that this is very different than the kind of analyses you get out of HAZUS. So kind of the data-driven approaches produce somewhat different interpretations of the probability of liquefaction than you might get from HAZUS. With respect to landslide deformation, we know that multiple potential modes of failure can develop large deformations and trigger landslides that can potentially damage facilities and infrastructure. So just from the 1906 earthquake, we see several different types of landslide failure modes: deep rotational slides, translational slides, rock falls, earth flows, and runout. And for each one of these modes, we develop a very simple model to capture that mode of failure on a regional scale. And we can look at different windows of size ranging down from 3 meters all the way up to 1,000 meters for different sizes of potential landslides and runout, and utilize that in a multi-modal landslide hazard analysis. Of course, there's a great amount of uncertainty in the strengths of the various geologic deposits when we look at the landslide hazard across such a broad region. So to assess the strengths within the context of the multimodal analysis, we utilize a maximum a posteriori optimization process with the available landslide database to help us back calculate strengths. We do this in such a way that honors the previously published strength values. There's been a number of studies utilizing laboratory data and back calculating strengths based on shallow disrupted slides to estimate strengths. And so we utilize this as a Bayesian prior in our analysis and then update on top of that. And when we do this, we tend to see that the maximum a posteriori optimization gets higher friction angles, a little bit lower cohesion than the previously published studies. And that's really a function of the influence of those deep rotational landslides, which often aren't considered in previous types of analyses. So how does this compare to real events? So we're starting with our site-specific evaluations, treating all the input parameters as random variables, and then going through the analysis. And so how does that compare with actual events? So for example, from the 1906 San Francisco earthquake, there was catastrophic damage in portions of the Mission District in San Francisco. I have a few photos here showing qualitatively about a meter of lateral spreading hazard at these locations. And that corresponds fairly well with what we would anticipate using the model. So I just want to note that the model is not calibrated to this specific event or any other specific event, but really we're just using the data, our site-specific hazard models, and kind of the geologic structure of the area. Likewise, with respect to landslides from the 1906 earthquake, there was catastrophic landslide damage at a few locations, particularly on the peninsula, just north of a point known as the Devil Slide. This is a quote from the 1906 USGS reconnaissance. There was a landslide of the whole face of the west end of Montero Mountain. And so we can see in an oblique 3D view here of the potential for very large landslide deformations to be initiated right around that Devil Slide area. Combination of shallow disrupted slides, rockfall, runout, and deep coherent rotational slides all kind of mobilize on this sort of slope. So a unique combination of different landslide hazard modes, each with their own kind of consequences for infrastructure and amounts of and magnitudes of deformation. This type of analysis can also provide some insight into what might be considered as an anomaly from historic observations. So for the 2014 magnitude 6 South Napa earthquake, there was a remarkable absence of liquefaction. This is a quote from the GEAR report. There's liquefaction really only at 2 locations, despite a very high peak ground acceleration. And so when we just look at the previous geology-based maps, we would predict high liquefaction susceptibility here, and that's not entirely what we're seeing. When we look at the data, however, we interpret that the Holocene alluvium of the North Bay is predominantly clay-like. So just looking at the data around the area, we would infer that the spatial extent of liquefaction is likely very low. The consequences are likely less. In addition, groundwater levels at the time were also very low. So we have 2 kind of factors that may have created less than anticipated liquefaction. 1, presence of a lot of clay-like soils, and 2, a lower than average groundwater condition at the time. So to summarize our regional scale liquefaction and landslide deformation analyses for the San Francisco Bay, we can extend site-specific liquefaction landslide models to explicitly address the great uncertainty in geologic and geotechnical properties across a broad region. These subsurface properties are often assumed to be scalar at site-specific. We know them with good confidence, but are now uncertain at a regional scale, and we can treat those as random variables. This includes uncertainties in groundwater, soil behavior classification, does it behave as sand or does it behave as clay, geologic structures, how thick are the geologic deposits, and of course the penetration resistance and strength. Through this process, we can simplify this to model the results using simple GIS-based raster functions. So the coefficients of the results of the smooth curve can be made into simple GIS-based coefficients that you can use in a GIS-based raster calculation with application for different earthquake scenarios. And the results of our study reasonably match observations from earthquakes such as the 1906 San Francisco and 2014 Napa earthquakes. Thank you for your participation here, and I think we'll answer questions at the end, is how I understand.
Yeah, that's right. Thank you so much, Mike. Very interesting work. Our next speaker today is Dr. Nico Kuhn. He earned his doctorate degree in geophysics from the University of Potsdam in Germany, where he worked on seismology. Dr. Kuhn then worked as a postdoc and research project scientist at UC Berkeley in earthquake engineering, and he's now a project scientist at the University of California, Los Angeles, working mainly on ground motion model development. Nico, please go ahead.
Thank you, Simon. So I'm just going to share my looks, sharing the screen. I hope everybody can see the screen. So I'm going to talk together with Melanie on generating spatially correlated ground motion scenarios. And I'll be mainly talking about the underlying sort of theory, and then Melanie is going to talk about the interesting stuff, which is the application. So basically what we want to do is we want to develop some suites of ground motion maps together with the associated rates that can be used as input for regional risk assessment. So we'll generate these suite maps and scenarios and give them to Alidad to do some magic with regional risk assessment. Because basically we want to have as input for risk, you want to have actual ground motion values, but they should also be kind of realistic, and we want to have them at multiple sites at the same time. So we don't want to just go to the hazard curve and pick some return period and pick a ground motion from the value from that. Because then what do we do if we have multiple sites? They're not going to all happen together at the same time. So we want to have something that can actually occur possibly in nature, but it should also be relevant, of course. So basically what we want is we want to represent and we want to sort of reproduce the seismic hazard curves at all the sites that we have within the Bay Area. But what we also don't want to have too many maps, because that would be then complicated for the downstream analysis to deal with. So I'm just going to start very simple with something we've all seen many times. So that has an integral, which is just integrating over different magnitude distance scenario, and then calculating for each scenario the associated exceedance probability for a certain ground motion level A. And the main thing that we can think of is that the integral is basically just an infinite sum, right? So the hazard integral is basically an infinite sum over many different magnitude distance scenarios. And then what we can do is we just truncate that infinite sum at some small number, and then we have an approximate hazard curves, which kind of sums up only contributions from some small finite set of scenarios. And then if we reasonably select those scenarios, we will probably get a relatively good approximation to the hazard. And then we just multiply each of those exceedance probability. So we can just calculate the exceedance for each scenario, multiply that with an associated rate for the scenario, and then we get our hazard. And then as a further approximation, instead of analytically calculating the exceedance probability, we can just sample from a ground motion model. So basically sample from a ground motion distribution with a certain median and certain standard deviation. given by the magnitude, distance, and other predictor variables. And then we sample multiple times, count how often our sampled values are larger than A, and then that gives us an estimate of the exceeds probability. And now we can also just include a spatial correlation model to just generate multiple samples at multiple sites for the same scenario, which will then give us something that's reasonable. And now we're basically almost where we are, because now we have some discrete set scenarios, and for each set of scenarios, we have samples at multiple sites. And if we choose, we just have a large number of sites, we're already there. The main problem, so that's basically Monte Carlo has, right? We just generate lots of groundwater samples for scenarios, and then we just count. And then we can also just have some, depending on the details, we can either have a discrete set of scenarios, we can sample from our magnitude distance distribution. Doesn't really matter. It will give us scenarios, and it will give us some ground motion values. Now, one problem is we need lots of samples to actually properly sample the tail of the distribution. So in order to get to like large ground motion values, and if we also sample from the magnitude distribution, we would sample lots of large magnitudes and get around that with maybe something like important sampling or whatever. But that's not really our goal here. What we want is we want to have these samples, but we want to have a relatively small-ish, and I think the different people would define small differently depending on what their needs are and what they can calculate. We want to have some small number of realistic samples, so that if we multiply each sample with an associated rate, and if that sample exceeds our target ground motion level A, then the sum of overall of the samples that we have will approximately the hazard curve. And ideally, simultaneously at all the times. So we could sample like hundreds of thousands of maps and then sample and then just select those samples that fulfill this requirement, but we're taking a slight fun route here. We only want to sample like those values that actually contribute to the hazard. And so basically what we need to do is, if we normally just sample from a ground motion model, we will sample many, many small values. There's a 50% chance that we will sample something that's smaller than the median. So if we just naively sample, we will not get to like the values that actually contribute to the hazard. So what we want to do is we want to balance our samples that are coming from our ground motion, sampling from our ground motion model, and we want to balance the fit to the hazard. But basically how we can interpret this is that our ground motion model is sort of like a prior distribution for our samples. It's just like a priori, this is how we would sample. And then we need to balance those a priori samples with a fit to the hazard, such that our approximate hazard, together with the associated rates and summing over all our selected samples, approximates the true hazard curves. Basically, that's basically just the method that we're using. We have a Bayesian model for the ground motion selection, which takes as input the number of maps that we want to have and the target hazard curve. And then we're just basically using our ground motion model together with the spatial correlation model as a prior for the ground motions. And then we use the fits between the approximate hazard and the true hazard curves, or the previously calculated hazard curves at each of our target sites. That is our likelihood. So we have to define some small probabilistic model for that. And with that probability, we can sort of define how well we want to fit the hazard curves. And then what we get is we get a posterior distribution of ground motion values at our target site. So we do this at multiple target sites. So that means we get multiple maps, and we also get a posterior distribution of the occurrence rates. Because we have to adjust the occurrence rates of each scenario a little bit to actually match the hazard, because they will not be like the a priori occurrence rates. And now what we do is we estimate all of this with Markov chain Monte Carlo sampling, because which gives us a number of us. So we don't just get one set of maps, we get multiple set of maps. And that's, from my perspective, that's very nice, because there's lots of variability in ground motion in the ground motions. And even if we have a small set of samples, we can fit the hazard curves with another set of samples equally well. And then the question is, does that matter? And if we have multiple posterior samples, we can investigate how much that matters. And if we maybe have to sample more, get more and more maps, or I mean, it's just always good to account for all sorts of uncertainty. And that's basically the method that we're using. And I think now Melanie will take over and show how we actually use this for the Bay Area.
All right. Thank you, Nico. It's always interesting to see the benefits of using Bayesian statistics approaches for these applications. Our next speaker is Dr. Melanie Walling. She specializes in ground motions and seismic hazard with applications to nuclear power plants and infrastructure. She works for geoengineers, where she performs seismic hazard assessments for their clients and pushes their seismic capabilities forward by developing new software and analytical techniques. Melanie enjoys the challenge of modeling natural processes such as earthquakes and then translating the seismic hazards into engineering design inputs. Melanie, the floor is yours.
Thank you. I'm going to kind of fly through these slides because I think the interesting talk is Alidad's talk that follows mine. If people are interested in more, you can contact me afterwards. So as Nico talked about, this kind of the methodology. And so in the implementation parts, it's like we optimize, and inputs into our optimization, the Bayesian optimization, are our hazard curves, are the control sites, which you can see here on the right. In red are the control sites, the number of maps. We also have to optimize over the ground motion level, because we want to make sure that we're kind of hitting our metrics. Inputs are kind of the representative scenarios. So we want to provide inputs that are kind of the important sources to hazard in the Bay Area, which I'll describe shortly. And then inputs into the optimization to our median predictions at these different control sites. And just so that you know that the number of maps, this 280, was selected as kind of the minimum number of maps needed in order to kind of generate realistic ground motions. We played around with maps, a lower number of maps, such as 100 maps, and we just found that there's a trade-off between kind of the lower number of maps you have, the less realistic ground motions you create. But we also don't want to create too many maps. And the ground motion level was set by kind of what the risk targets, like what was important to the risk. And so next I'll discuss the representative scenarios. There were 14 parent scenarios. They were developed from a deaggregation using the USURF3 model. On the left there is a table of our 14 parent sources with the magnitude. On the right here is a map taken from the USGS website, which basically shows kind of the locations of the major contributor faults in the Bay Area. And so you have Calaveras, which is shown in blue on the map, and that takes, in Concord and Greenville, that takes about 16% of your hazard for the Bay Area, or the 26% that's shown in purple. And then you've got Concord, Green Valley, and Greenville shown in blue, takes around 16% of your hazard. You have Hayward, and shown in orange, taking around 33% of your hazard, and then San Andreas taking around 22% of your hazard. So these were our parent faults, and from each of the parent faults, we created 20 maps per parent fault, which in combined created our 280 maps. Once we had these, once we performed the optimization on the 213 sites, we needed to interpolate those to the 3,000 sites to make sure that we actually created a map of the ground motions that we want for this risk target. We interpolated these using kind of the spatial correlation model from the Latham-Baker, and then also sampling from a multivariate truncated normal distribution. And so shown on the bottom here is just median prediction ground motions in the colors, and then you can see on the black, which are the 13 sites. And then once we use the spatial correlation function and with the optimization results, you get the map shown on the right, where you have you can see the kind of the spatial correlations, the variability, and then you also see kind of like the locations of the 13 sites, 213 sites. The reason for the multivariate truncated normal distribution is because when we were sampling realizations, we couldn't sample the really tails of the normal distribution because it would create unrealistic ground motions for the risk. And so we moved to truncated. Here is some examples of the results for two different scenarios. So scenario 1 is the San Andreas. Scenario 3 was the Hayward. On the top row is median predictions, and on the bottom row is actually the realizations. So the bottom row is where the results are. And this is for just showing you two different kind of examples. And I think the point of this plot is that, if you were just to use median predictions in the risk assessment, you have unrealistic ground motions. It's just too smooth. And so by incorporating a spatial correlation model, you're able to kind of develop these kind of more realistic looking ground motions. Again, if the San Andreas went off, we wouldn't expect to see maps from the top, or the Hayward went off, but we would be looking more like maps from the bottom. And so from here are the kind of two different sites, results from two different sites. But from all the different sites, it looks very similar from that we were sampling. On the black is our target. The different colors, hazard curves, those are our 40 different posteriors. So we calculated, we did everything with Stan, R, and Python, but we had we had in total 40 different posteriors. Each posterior had 280 maps. And then these are kind of the results. And so the main takeaway here is that we have a really tight fit to the ground motions that are important to us. And then you have a slight deviation from the target hazard curve, but at the ground motion levels that are less important to the risk. And at the bottom here is just kind of a plot of the density of the residuals from there. And you can kind of see where that looks like. Once we had the interpolated maps to the 3,000 sites, it was important that we had to correct for site-specific events in order to get site-specific ground motions. And so we did that by creating site correction functions at the different control sites, which is shown at the bottom. We calculated these as the ratio of the USGS hazard curve to the VS30 to the VS30 of 1080. And then from using Eric Thompson's VS30 map of California, we had the VS30s at all the sites, and then we can use the amplification functions at the control sites to interpolate using the ground motions from the 1080. We would go into these interpolation functions and then pull out the amplification. On the right-hand side and the above plot, that's an example where we, for a site with the VS30 of 381, And so the different hazard curves there are the different posteriors, and it's covering the target hazard, which is kind of shown below. And shown below is, in blue is the target hazard. And then the red is the mean of all of the different posteriors. So you can see that, that we're matching the USGS target hazard with having site-specific effects. And this is kind of what we wanted. And then this is my last slide. So this is our discussion, is that, you know, this was a long process to kind of get to where we're at. This sensitivity, you can't ignore the sensitivity to the number of maps. Again, there's a trade-off between how realistic the ground motions can be and the number. Getting to the multivariate truncated normal sampling was important because we were sampling tails at one point and creating too large a ground motion. So this was a key. There's a sensitivity to the spatial correlation model. We looked at model with the nugget and without the nugget, and they have pros and cons for each of them. And then from there, I think the next step is that we feel pretty comfortable with what we have in our methodology and our approach. And so now the matter is extending this approach to multiple periods using a co-regionalization model. So we can develop PGA and 1 second maps, or PGV and PGA 1 second maps that are correlated in space and on cross-spectral period. And that's it. Thank you.
Thank you, Melanie. So we're running a little bit behind time, but we will stay for 10 to 15 more minutes so that we have time to complete the presentations and also answer the questions from the audience. Our next speaker, last but definitely not least, is Dr. Alidad Hashemi. He graduated in 2007 from UC Berkeley. He specializes in structural modeling, dynamic analysis, SSI, and seismic risk analysis. Dr. Hashemi has been with HE3 since 2019 and with Bechtel before that for about 13 years. He also served as a lecturer at Cal between 2013 and 2020. Alidad, please go ahead.
Thank you, Renan. So very quickly, I've never been to a group discussion and presentation that finished in time, so this one is not going to be an exception, unfortunately. But I'll try to go through my slides fast, and I'd be happy to take questions later in email or if you have time at the end of the panel. So very quickly, our goals basically are to do seismic risk evaluation for a portfolio of assets using realistic regional earthquake scenarios that Melanie and Nico talked about. And in doing so, we want to be able to calculate and quantify seismic losses and quantify seismic risk. What we do is that we sort of calculate a risk score. And we want to be able to do this both on building by building basis and also for the entire portfolio. The main reason to have these results on a building by building basis is that you want to be able to later rank these buildings and assets, other assets if you have, and then be able to prioritize them and look at, think about further studies if needed or mitigations of risk as necessary. So the portfolio that we're looking at is the building assets that Albert mentioned. It's the PG&E CREST database. So it includes somewhere in the range of 750 buildings. These include office buildings, maintenance facilities, control buildings, and warehouses. And from those, all in Northern California, from those, about 193 of them fall within the scenario range that Melanie and Albert talked about. And for those buildings, as part of previous studies, we had developed vulnerability functions. So these vulnerability functions essentially relate the casualties and costs and losses to the PGA or to some ground motion intensity measure. In this case, we're using PGA because that's how we have the maps. But there's a lot that goes into coming up with those vulnerability functions. So first of all, we try to use the information that is available. as you might guess, for the amount of information that we have for these buildings in this database is varied quite a bit. It ranges from having sort of ASCE 41 type evaluations, tier 1, tier 2, or tier 3. We are very lucky type of evaluations that we can directly use to develop fragility functions, and then from there on to vulnerability functions. Or we might have design calculations, or in some cases, performance-based design was done in recent past. So we have a performance objective for the building that we can then use to construct the fragility functions. And the other, if we don't have these things, then we would need to rely on more basic information about the building. What is the building type? Do we have concrete, steel? Is it a moment frame, shear wall, whatever? And look at the footprint of the building, look at the number of floors, number of occupants, location of the building, site class, building code year, things of that sort. And then try to estimate those fragility functions for different damage states for the building. And combine that with the non-structural content for the building that in some cases are known, in most cases estimated, depending on the use of the building. And combine all of that with sort of a cost model that we have calibrated based on the information provided by PG&E for this particular portfolio. And then get all of that information together and try to estimate that casualty versus PGA function, and also the cost of earthquake losses versus PGA function. So those are essentially, it's an example of such vulnerability curve that feeds into the calculation. So the other input to our analysis is the earthquake scenario that Melanie and Nico talked about. So as Melanie mentioned, we are using 280 earthquake scenarios. So I'm just showing this as a perspective of the user for those. And each one of these scenarios is described for a grid of about 3,000 points. We have latitude, longitude, PGA values, and the rate of occurrence for that scenario. You could then use that, collectively use the 280 scenarios and calculate the rate of exceedance for a given PGA values, and then plot them in one curve, which is essentially the hazard curve implied by those sets of maps for those sets of 280 scenarios. And then you can compare that with what you would have from USGS at the location of each building. So this is, again, another example. The blue dots on the plot show basically where the hazard curve that is implied by this set of maps. And the red line is the USGS hazard curve. And we do have a target range for this matching. So in this case, we're looking somewhere around 0.05 G to 20,000 years, so 5 times 10 minus 5 to match the USGS hazard curve. And I'll refer back to this plot in a couple of slides, just to show you that at least for the assets that we have, this range seems to be adequate. So we have the vulnerability functions, we have the hazard curves. Next step is to go and actually quantify seismic risk. And to do that, we need to be starting from vulnerability function, but the consequences are different than those losses. So there's a nonlinearity inherent because we need to account for compounding effects of concurrent damage to multiple assets. So that essentially is the difference of having one building or different buildings damaged in different events, or having one event that damages several assets. So when you do have that scenario that one event would damage a lot of different assets, then going through recovery, going through mitigation is going to be much more difficult. So that this nonlinear scale factor is there to reflect that fact. And once you have those consequences with the nonlinear scale factor, then you can do a calculation of that risk score, either do it building by building, sort of the more traditional way, looking at the hazard curve at the location of each building, and calculate the losses and calculate the consequences, and from there the risk score. or you can look at the entire portfolio together using these type of earthquake scenarios that would enable you to do such a thing. So jumping again quickly to the results, basically we are going through that exercise in 3 ways, and we are calculating seismic risk score for safety separately, for financial losses separately, and also putting them together as a total risk score. Again, this is particular to this set of assets. So if you were to have different assets, you would need to account for different type of losses. And for each one of these, we are looking at each building on its own, using the USGS hazard curves. So that's sort of the traditional way of calculating seismic risk for different buildings. And then we do that's the blue bars essentially. And then we do the earthquake scenario-based approach. So now we are looking at the entire portfolio. We are calculating the consequences based on the losses on the portfolio level and calculate those. And the third one in green is if still the traditional way, but instead of looking at the USGS hazard curve, we would be using the hazard that is implied by those sets of maps. And the reason we are doing this is to show that for the range and the target range that we used and the scenarios that Melanie and Nico provided, we do have a very good match between USGS hazard curve, which uses the full range of hazard, and us using those 280 scenarios. On a building by building basis, they match, so the range is adequate for matching the hazard. But then when you look at the difference between what we get out of the portfolio-based evaluation, looking at the entire portfolio using scenarios, you see that there's a large difference, almost a factor of 2, and that really reflects that nonlinear scaling of consequences. The fact that having a lot of assets damaged in the same event is a much more catastrophic event than having different assets damaged during different events. So that's basically the way to capture that, and you can see that this effect is really significant. You can look at the same idea, but look at it building by building. So again, here I'm plotting the building by building risk score versus the portfolio-based risk score. And each dot represents one of those 193 buildings. And you can see that almost all of them are sort of tilted toward the scenario-based. So you looking at the portfolio would show much more risk per building. And then the other interesting trend is that if you have buildings that by themselves, they have very high risk, then this effect is going to be less for them because they're more important. The relative importance of the rest of the portfolio to them becomes less. And another interesting observation is that if you take the ratio of this portfolio-based evaluation of risk to building by building and try to look at the geographical distribution of those ratios, you see that basically if you have buildings that are sort of alone or farther from other buildings, that ratio for those buildings is relatively smaller. And where you have building clusters, when you have many buildings next to each other, that geographical correlation of ground motion parameters causes a correlation between the damage for those buildings and thus increased risk for those. And finally, if we were to look at the ranking of the buildings, again, if we do that ranking building by building, which is the blue and green curves, bars that are shown here, you can see a descending order in this case. But if you were to look at the portfolio-based ranking, you can see that even the order of ranking and prioritization of those buildings would change, basically favoring the clusters of buildings and showing them as higher risk in general. So with that, let me stop here. and I'll be happy to take any questions or comments.
Thank you, Alidad. Albert, back to you.
Hello. So I just wanted to quickly wrap up and just say that there's more work. You've seen some topics, but there's more work to be done here through partnering with other utilities, agencies, municipalities, and sharing the approaches that we've outlined to start thinking about the SF Bay region in its entirety and how we can coordinate emergency response and preparation for events. But we also need to expand and refine the regional models beyond the Bay Area. And so that we can start thinking about PG&E can start being more quantitative in the risk assessment for all of its assets in the same approach, but now territory-wide. And with that, I'd like to thank the speakers, Alidad, Mike, Melanie, and Nico for volunteering to put this together for me, and open it up to any questions that we have.
Yeah, thank you, Albert, and thank you to all the speakers for putting together this great presentation. It's so interesting to see so many tools and techniques combined together to get this product. So we have some questions in the Q&A. I will just read them, and please, whoever feels that is more relevant, please just go ahead and answer. So we have a question here saying the nonlinear scaling of consequences seems to have a significant impact on the results. Can you tell us more about how the scaling function was calibrated? I think this is related to Alidad's presentation.
So,
yeah.
Albert, do you want to take this?
So, I guess I would say from the owner's perspective, the nonlinear scaling depends on how risk adverse or risk permissive you are. And so there's been a lot of discussions with our enterprise risk team about what should this nonlinear scaling feature be and what are its impacts. And so there are different ways that you can think about risk management, and this scaling factor would then influence the risk calculation. I'll throw it back to you now if you had more.
No, thank you. I was just going to punt and say that this is essentially a PG&E decision. And I see the other question is also related as to what we mean by the risk score. So it's essentially a indexed calculation of the losses that you would try to bring it to a number that is better understood, as opposed to, say, number of casualties or dollar amount of annual losses. But again, the specific method to calculate that risk score is something that PG&E does, and we are doing it consistently to their approach for this study.
And the scaling and risk score process are defined by the CPUC or interactions with the CPUC, and we use the risk score for prioritization of work. So it really depends on the asset owner in terms of what their acceptable level of risk was, and also what does risk mean to them, and is it just financial? Are there safety implications? Are there reliability implications that they have?
Sounds good, thank you. So given the time, I just like to emphasize that these tools will become available, and Albert or any of the speakers, if you would like to elaborate more on how people can have access to your work, tools, and publications, please go ahead.
Yeah, I would just say that the geotechnical modeling, I think there's some potential legal issues that we'll have to resolve to make sure before we distribute them. And then the ground motion scenarios, I think, would be distributed through the journal article that would follow, that Melanie and Nico are in the process of finalizing.
All right, thank you. Yeah, I would encourage everyone to follow up with specific questions with the speakers. For now, I will just give it back to Elizabeth for closing the webinar.
Great. Thank you again so much to everyone who attended, to all our great speakers. I just want to take a brief moment to request that you complete the post-webinar survey. It should pop up in your browser as the Zoom ends, or you'll also get it by email tomorrow. You can learn more about EERI at our website. And if you want to help support the work that EERI does, particularly through our Learning from Earthquakes reconnaissance program, you can donate to the LFE endowment. And then finally, I just want to acknowledge that this webinar series and many other activities we do are made possible by funding under a cooperative agreement from FEMA, as well as by EERI members and the LFE Endowment Fund. Thank you so much for joining us today.